I'm replacing a compressor, a coil, an indoor coil, and an outdoor fan motor on the same package unit. Yeah, it's a lot of failures on one unit. Let me show you. Just used the torches and unbrazed the suction and discharge line from the compressor here. I'm going to take this compressor out now. And this is the indoor coil that was leaking. Little thin indoor coil, evaporator coil. And I just used my torches. I've got that connection loose, and then this connection, this right here, is the metering device for the evaporator, and I'm going to put a filter dryer between here and here in the liquid line, and this is the metering device for the condenser section, condenser and evaporator. I've also got a fan motor here, and if you move it side to side, you've got slack, and so those bearings are bad. Got a fan motor here, source one. I'm going to get this thing put back together now, put the new compressor in because that one had mechanically failed. It was locked up, would not start. Then I'm going to replace that leaking coil there. See, I've got a coil, new compressor. I'll show you everything when I get it put back together. And if you guys have any questions on, what you need to replace these two components or just general information, let me know. Alright, so I got the new coil welded in. See that connection there? That connection, the filter dryer is in. It's a biflow because it's a heat pump. Look at the new coil. Old coil doesn't look like this. Look at that. New coated coil, looking good. See, this old coil does not have. See that? That's the old coil. And then got the old compressor in here. See, it's quite large. Quite large Copeland scroll, same size, but as far as capacity, but this compressor is quite smaller. Look at that. New compressor's in, new coil's in, filter dryer's replaced. Now I gotta change the fan motor and have this thing back up and running. So I've got the nitrogen on around 300, high side and low side, and I'm just holding the pressure at 300. That way I can make sure it doesn't leak. You gotta have nitrogen to pressure test to be able to also remove the non-condensables before you put on the vacuum. So I got the nitrogen on. I wanna show you right now the most replaced motor. This is the most replaced motor in my opinion. I have replaced at least 100 of these motors on these York units. Motors made by Gentech, and it is a 1/4 horsepower 850 RPM condenser fan motor. Had to get some sandpaper to sand the shaft to get the actual hub to come off of the shaft. So make sure you have some sandpaper with you. Definitely need some sandpaper. All right, so I'm gonna vacuum it down. First, I'm gonna replace this motor. If you see this right here coming out of the motor, then it's likely that the bearings are going to be going bad before too long. It's going to start creating some rough movement here when you try to move the shaft. So side to side, if it's got slack, bearings are bad. If you move it and it's rough when you turn it, you can't really turn it, that means it's bad. Also, this right here, this oily dust here that comes out of the motor, that right there is an indication your motor's going bad. New motor's on. I've got the fan blade in the right position on the shaft. That way it's rejecting heat out of the top, and you'll have to check the amp draw when you start the unit up. That way you make sure it's not pulling too many amps, because it could be in the wrong position if it is pulling too many amps. So you'll check run load amps on that motor when you start it up. I've got it wired in. Make sure you have some wire ties with you, and don't leave any of these wires against the discharge line where it could burn through the wires. That's a terrible mistake to make. We're holding the nitrogen nicely on the low and high side. Got it hooked up, and I'm gonna go ahead and let the nitrogen out and start pulling a vacuum. Got my vacuum pump. I'm just gonna take my yellow hose and hook it up to the vacuum pump, and then you're gonna see that it's gonna start pulling into a vacuum. Then we're gonna have this thing up and running. So I got the gauges hooked up to the vacuum pump. We got low and high side hooked up to the package unit. And then I've got my pump hooked up and you can hear it sucking. So we're in good shape. Now it's pulling into a vacuum. I'm gonna go run and get a harness for this compressor, and then when I get back, it should be pumped down. Make sure that you do a triple evac. If you don't know what that is, it is where you take and you pump the unit down for 15-20 minutes. You put nitrogen back on and you put it on a low setting, 15 pounds, just to break the vacuum, and then you do that again. And that helps to pull down to the microns that you need, which is, you know, usually around 500 microns. If you don't have a micron gauge, get a micron gauge. I'm back. I got the plug for the compressor and sounds like it's done pumping down. Now, if you don't have a micron gauge, then a good way to know that the vacuum is working and it's vacuumed like it should be is you just basically turn off the manifold, go into the pump. You didn't hear it change sound, did you? Okay, shut it off, turn the pump off. All right, so after you vacuum, you shut your gauges off. And if you have a micron gauge on, the micron gauge will begin to rise if it's leaking. So if it's at 250 after you stop, then you shut your gauges off, turn the pump off, and it goes up to 500, 1,000. You know it's leaking still. If the pump changes sound when you turn the pump off, then it still needs to be vacuumed. If you see that in vacuum there, see, vacuum, it's in a vacuum, then it shouldn't move after you turn it off. If it starts to rise up, then you have a leak. So these are things you need to know in the field. You know how to hook your pump up, you need to have a good micron gauge. Got my scales, field piece wireless scales. I'm going to charge the system up. Always charge upside down so you have liquid, and charge through your high side. Filling up that condenser section there. Also want to do factory charge. So I'm going to put in 6 pounds and 0 ounces. Zero my scale out and then start adding. We're adding through this line here. If you can't find a plug, a receptacle with power on site, make a cord so that you can pull power. Whether you're taking that power from the equipment in there, some of the electrical components like just the line voltage coming in, there's some terminals you could probably put this side on. Remember, 115 volt pump, it's only going to need one leg of 230 and then the other would go to ground, okay? So if you wanted to make a cord, make a cord. Get some SJ cord that's the right size. I think this is like number 10 wire, and then you would just take and you would hook one side here. This is a 230 volt package unit, and then the other side to ground. There we go. And then of course you'd have to turn your breaker on. So probably you can take it from any location. Just make sure that you have a disconnecting means. That way it's safe. This can be unsafe, so definitely wear PPE if you have to. Consult your physician. Definitely try to take it from the breaker box if you have to, if you don't have a receptacle. This right here can help you out. Make your own cord. I misplaced my micron gauge like most of my tools. When you get in a hurry in the field, you lose all your stuff, which is great. So I use field piece. It's a nice micron gauge. Look at it, it looks beautiful. But of course, I don't know where it's at. That's great. I'll probably find it here in a minute. How do we check inrush current? With the field piece meter, you put it in line with VAC, AAC. You push select, and then you push inrush right there, that button. Let's see what happens. New compressor, new indoor coil, new outdoor fan motor. This is practically a brand new unit now. Wow, 13 amps on startup, 13.92. Very nice. Correct refrigerant charge is very important. In undercharged systems where there's not enough refrigerant, the compressor is overworked and it may operate continuously. That leads to wasted electrical energy and also poor refrigeration. Also, with a lack of refrigerant, you can have an increased liquid line and drier temperatures. As a result, the dryer heats up and some of the moisture it has collected may be released back into the system. In an overcharged system, where you have too much of a volume of refrigerant, you may have excessive head pressure in the system, also leading to compressor damage. So we want to make sure that we have a good method to check refrigerant charge. Today, I want to show you what tools you need, and I want to show you the method I use. There are a number of ways to determine if the refrigeration system has the right amount of refrigerant. And what I would like to talk about today is subcooling and superheat. Today, I want to check charge by subcooling and superheat. The subcooling method is generally used to check charge in systems with a thermostatic expansion valve, or a TXV. The superheat method is used to check charge in systems with fixed orifice metering devices, such as capillary tubes. These two methods can be used to check refrigerant charge as part of the troubleshooting process or after system charging to ensure that the proper quantity of refrigerant has been added to the system. Let's go into what we need. Let's talk about what I'm doing here. I'm using a temperature probe and my meter to check the Fahrenheit temperature of my liquid line and my suction line. I'm going to be taking that temperature probe and connecting it to the suction line close to the compressor inlet, and then I'm going to also connect that temperature probe to my liquid line. I'm connecting the suction line to check superheat. I'm connecting to the liquid line to check subcooling. Let's talk about checking refrigerant charge by subcooling, start to finish. We turn on the refrigeration system. We let it run 10 to 15 minutes. We ensure there is proper airflow through the condenser and evaporator coils. We take a high side pressure measurement, which gives us the PSI of the high side. We use that head pressure measurement to determine the temperature of the refrigerant in the condenser. There are two ways of doing this. Some high pressure gauges have displays showing saturated refrigerant temperatures. You see this? This is the saturated refrigerant temperature. That correspond with the pressure measurement. If your gauge does not have this, check a pressure temperature charge. That shows the corresponding values for the refrigerant in the system. Record the saturation temperature. You measure the temperature of the liquid line near the metering device. When using a temperature probe, firmly attach the probe to the pipe and insulate the probe to get an accurate reading, not affected by the surrounding temperatures. You record the liquid line temperature. So now we've recorded the saturation temperature. We've recorded the liquid line temperature. To determine the subcooling value, you subtract the measured liquid line temperature from the saturation temperature value, and that equals your subcooling. Saturation temperature minus liquid line temperature equals subcooling. Then you can look up and record manufacturer subcooling value. Now let's talk about checking refrigerant charge by superheat. You turn on the refrigeration system, you let it run for 10 to 15 minutes. You ensure that there's proper airflow across the condenser and evaporator coils. You measure the dry bulb temperature of the ambient air surrounding the condenser coil. You record that dry bulb temperature. Then you measure the wet bulb temperature of the return air just upstream from the evaporator coil. Record the wet bulb temperature. Record the dry bulb temperature. Look up the target superheat for the system based on the temperatures of the ambient air outside and the return air inside. Record target superheat. Now, take an evaporator low side pressure measurement using the blue low side gauge. You get your PSI. You use the evaporator pressure measurement to determine the saturation temperature of the refrigerant in the evaporator. There are two ways of doing this. Some gauges display showing the saturated refrigerant temperatures that correspond with the pressure measurement. If your gauge does not, you just get a PT chart like I talked about when we were checking subcooling, and you look and it shows the corresponding values. Record that saturation temperature. Now, measure the temperature of the suction line near the compressor. When using a thermometer with a sensing probe, secure the probe to a flat, clean area of that suction line and wrap it in insulation. This practice will prevent ambient air from affecting the temperature reading. Superheat and subcooling calculators are useful for this step. Record that suction line temperature. After you record the suction line temperature, subtract evaporator saturation temperature, determined by the pressure measurement, from the temperature of the suction line near the compressor to determine the superheat value. Suction line temperature minus evaporator temperature equals superheat. Compare the calculated superheat value to the target superheat for the measured wet bulb and dry bulb temperatures. Record any difference. If the superheat is low, the problem could be a malfunctioning metering device, inadequate airflow through the evaporator, or an excessive refrigerant charge. If the superheat reading is too high, the problem could be a restriction in the liquid line, a malfunctioning metering device, moisture in the system, an excessive heat load, or an inefficient refrigerant charge. Once the target superheat is found, it is compared to the actual superheat, which is determined by the evaporator pressure and the suction line temperature. I want you to think about each coil individually and think about them being dry, which means they don't have enough refrigerant, or being flooded, which means they have a lot of refrigerant. And I want you to make sure that you understand that if I don't have a superheat that's 10, that if I have a superheat that's 100, then that means I need to add more refrigerant. If I have a superheat that is 0, then I have too much refrigerant. And I want you to also understand that if I have a subcooling that is 30 or 40, that means I have too much refrigerant. And if I have a subcooling that is 1 or 0, that means I don't have enough refrigerant. I want you to make sure you get that in your head before we move forward. As I'm making all these checks right here, you're going to be able to see these relative liquid temperatures and pressures. So by the end of this video, you ought to be able to go to another system and be able to check refrigerant charge efficiently, knowing the values that you have to achieve for the system to have coils that have enough volume of refrigerant to be able to operate efficiently. While you're checking your superheat and your subcooling, use a temperature probe in the duct. That way you can measure the temperature split between return and supply. You want around 20 degrees on this residential package unit here. This is where the blower is. Blower speed's going to affect the amount of airflow on the coil and therefore affect the temperature split. So if you raise the fan speed 1 degree from, low to medium or medium to high, then you could lose a couple degrees in your airstream here for your temperature split. So you can use a little temperature sensor here that plugs right into the field piece meter, or you can use a dual end duct psychrometer. These probes have seen better days. I actually broke this one, and the other one I broke, and I've got to get new ones, so I'm going to order those. But check your temperature split while you're checking your liquid levels in each side of the coil, the evaporator coil and the condenser coil. Make sure you check the temperature split. The closer you get to having flooded coils and having right liquid levels in each coil and the amount of refrigerant that you need, the closer to the temperature split you'll get. So you will achieve temperature split the sooner you get all of the liquid right inside of the equipment. And we need to make sure we have factory charged 6 pounds. And that's why I have scales. So you need scales. Knowing superheat and subcooling is important because it allows you to be able to know whether to add refrigerant or to recover refrigerant. For example, so far we've added refrigerant and our target superheat is between 10 to 15. We've added refrigerant and our suction line temperature has decreased. Our low side pressure has increased. Our superheat was 50 and now it's dropped to 30. So we're getting closer to our evaporator being filled with liquid. So the superheat is how much liquid is in the evaporator. The subcooling is how much liquid is in the condenser. You can tell that both pressures, low and high side, have increased. And now our subcooling is around 12, whereas we needed a subcooling of around 10. So that means we're reaching the point to where we know that our unit is almost charged. A little bit more knowledge on 410A. 410A has operating pressures that are 40 to 70% higher than R22 systems and often requires a new compressor with thicker walls which can handle the higher system pressures. In addition, R410A systems require thicker ACR tubing and a condenser rated for use with R410A. R410A must use POE lubricant, and a single oil change to POE will still leave a significant amount of residual mineral oil in the system. A single package machine like this has a specific refrigerant charge that can be taken at face value. A split system, however, will have a refrigerant charge amount that is conditional on the distance between the condenser and the evaporator. You need to liquid charge with 410A because it's a zeotropic refrigerant. Initially, the refrigerant is liquid charged into the high side of the system. When the liquid line is filled to capacity, the remaining liquid is charged into the low side of the system. And most technicians use the same process to quickly charge individual refrigerants. But this is not recommended because of the risk of slugging the compressor. You must know that liquid refrigerant into the low side is not good for the compressor. So you might need to use a special metering device in between the service hose and the low side service valve. I will be charging factory charge and then today through the low side for learning purposes only. I want you guys to understand exactly how I use superheat and subcooling methods and how I check using the values that I'm given. Notice the suction line temperature and the liquid line temperature now. There's a greater difference between the two measurements, and that is because both of our values, superheat and subcooling, are coming into the range which we need for us to know that both our evaporator and condenser are being flooded so that we have the total volume of refrigerant that we need for this unit to operate correctly. And you're going to notice in the field with air conditioning systems using 410A that the 40-degree temperature difference that we have between the suction line and the liquid line are going to be relative. You're going to begin to check these values and monitor more and more and realize that when you start to have the temperature drop of the suction line, then you're going to be able to know when your unit has enough refrigerant. If you want to take more time to look at the measurements I put on the screen, pause the video throughout, look at those measurements. If you guys have more questions, leave those in the comments. I really appreciate the support. If you like this video and you thought it was worth $1, go check out my Patreon right now. Become a patron. I've got tons of videos on there exclusively for people that are my patrons. I want to help you guys to learn more about the service industry, the field, being a better technician. Thank you for supporting me, guys, and I hope you don't forget, I'll keep you cool if you let me.